Hi, my name is Pedro Miranda and I'm here to present the paper, an analysis of Monte Carlo simulations for forecasting software projects. Uh, this paper was written by me, João Carlos Pascoal Faria, Filipe Figueiredo Correia, Ahmed Fares, and João Mendes Moreira from Engineering Faculty of Porto University and Ricardo Graça from Fraunhofer, Portugal. The context and motivations of the paper are that software developers can't usually forecast accurately the effort or delivery date of the project to be developed, a problem that is inherent to the uncertainty that underlies their activity. Changes in the project during its development will cause delays that will affect other teams and that may end up in a delay in the delivery that this could break the stakeholders' trust in the company. Data-driven forecasting methods are increasingly used, but there is still little evidence about their effectiveness, namely in agile contexts. The objectives of this paper are to study the feasibility of using the Monte Carlo method to achieve accurate forecasts, to understand how the accurateness of the Monte Carlo method varies with the amount of historical data used and with the amount of work to be forecast, and to implement different approaches and evaluate them with real projects and study their efficacy and accuracy. So we identified four main types of forecast and estimation methods. These four types are the empirical methods, methods that gather information by means of direct observation and experience, the theory-based methods, methods based on an explicit theory or logic model, the regression methods, statistical methods for calculating the relationship between a dependent variable and one or many independent variables, and the machine learning methods, methods that work with the machine learning and focus on the learning ability inherent. As a revision of the state of the art, we choose 9 main methods that already exist. These methods are the Angel method, the White Band Delphi method, the Planning Poker method, the CRSAM method, the Kokomo, the Monte Carlo, the Slim method, the Bayesian network, and support vector machine methods. To classify these 9 methods, we used 4 characteristics: the ease to collect the input data, the accuracy of the output, the applicability in agile context, and the ease to understand the prediction made by the method. In this chart, we can see the results of that classification. With green, we have the characteristics where the method is good, provides good results. With orange, we have the characteristics where the method, although not being good, is satisfactory. And with red, we show the characteristics where the method provides bad results, so the characteristics that are limitations of the method. As you can see, the Monte Carlo method is the method that provides us the better results with all green. The machine learning methods, mainly the support vector machine, also provides good results in the first 3 characteristics, but the method is not easy to understand, and the predictions are not easy to understand how the method achieved those predictions. So we choose the Monte Carlo method, and to implement it, we use a data set with real data from a set of teams working using sprints and managing work using user stories. This data set is divided in the data set has projects. The projects have stories, and the stories have information about the status that could be in progress, done, or others, the resolution date, and the effort estimate made by the users. The stories are developed in sprints who have a start date and end date. We also have users who take part in stories. We have reporters, creators, and assignees. That these last ones that work on the development of the story, and we also have changelog items that keep the information about changes made to the story. So in the summary field, we have which field of the story class was changed. We have the from field that tells us which field of the story what was the original value of the field. We have the to field that tells us the update value that we want to have in that field of the story, and we have the date of the change. We also have the authors of the changes. With this, we used two different approaches: the takt time and the effort. We also have the duration in this chart to be easier to explain the other two. So the takt time is the time between the completion dates of successive stories. So in this case, we have story 1, 2, and 3. We can see that the takt time measures the time between the end of story 1 and the end of story 2. And the next takt time will be between the end of story 2 and the end of story 3. The effort measures the amount of hours the developer assigned to the story spent working on the story. This is calculated by the amount of other stories this developer assigned to this story was also assigned to and working on, assuming that he works 8 hours 8 hours per day. So as we can see, the story 1, we can see that the effort is a little bit less than the duration, because we know that in the user story we have time losses. The effort for user story 2 and 3, we can see that the effort, the user starts with all of its effort on story 2, and when story 3 starts, we can see that the effort is split between the two stories, and then when the story 2 ended, we can see that the effort of the user was all put into story 3. With these two approaches, we developed a Monte Carlo method that takes as input the confidence level, the number of stories to forecast, and the historical data, both takt time and effort. We have inner and outer cycle. The outer cycle will execute 200 times, and this will provide us with a list of 200 values. Each of these values will be calculated in the inner cycle. The inner cycle will execute the number of stories we want to forecast for, and starting at 0, we'll add for each story a random value from the historical data. In the end, we'll have of the 200 executions, we'll have a list of 200 values, as I said, and we'll sort them. And since we want a confidence level in this case of 95%, we'll remove 2.5% at each end of the list. We'll then calculate the median, the mean, the lower bound, and the upper bound, meaning the lower and upper bounds, the minimum and maximum of the list. Our forecast is the median of that list. Here we have some example outputs for takt time and effort. For example, if we want to forecast for a single user story, we'll have the outputs of the left. If we are forecasting for a set of stories, we have the outputs on the right. As we can see on the right, we have the sprints in the takt time example. Since with takt time we have a continuity, so we have the historical data at green, and then we continue to the rest of the project on the first point after historical data. On the effort, we don't have that, so we start at 0, and we'll say for that number of stories we will have a total effort of, and that will be our forecast. To evaluate these approaches, first we made 3 experiments. Firstly, we made the takt time forecast for a set of stories. This experiment was made to calculate the takt time accuracy for this set of stories. In this experiment, we had 10 experiments, and as we can see, we have the forecast on the left. We have the forecast for each of the experiments, and we can see that the real delivery date is always within the forecast range for all the 10 projects. So our confidence interval is always including the real delivery value. And on the right we have the magnitude relative error and the relation to the number of historical stories used. As we can see, in some points we can say that there is a relation, but this relation on the beginning of the graph is not so clear, since we have times in this graph that where the historical number it's higher and the error is lower, and on the other end we have different cases, so it's not so easy to understand this relation. The mean magnitude relative error for these 10 experiments was 32% as the final accuracy for these 10 experiments. Next, we have the takt time for historical and forecast numbers. This experiment was made to calculate the ideal number of historical stories and of stories to forecast. We start with 5 stories, and we have a percentage error for each number of forecasted stories, of each number of stories we want to forecast. So we can see that we start with 5 and the error is a bit higher, and as we increase the number of historical data, we can see that the error starts to get lower. In here the lines are getting closer, so we are achieving a ideal amount of error. And then when we add too many stories, we can see that the error starts to increase again, and finally we present the 5 best results, where we can see that the line with where we use the 45 stories as historical data and forecasting for 60 or 65 stories was maybe 65 stories was the ideal window. So using 45 stories as historical data and forecasting for 65 stories was the ideal, provided the lower error. The last experiment was the effort forecast for a set of stories, and in this experiment we analyzed the accuracy of the effort approach when forecasting for a set of stories, and we compare it with the user's estimated that was provided in the data set. Since we didn't have a large number of projects with these users estimates, we in this experiment we only have five experiences. We see that when forecasting for many stories, some forecasts will get out of the confidence interval. We, like for example the first case where the real effort was higher than the confidence interval maximum, since we were forecasting for 100 stories. We can see that the model provides good accuracy with the mean magnitude relative error for the 5 experiments of 20% for our model. and the model is also way better than the user's estimated provided, with the user estimated having a mean magnitude relative error of 134%, showing this way that this model was beating the user estimated in all of the projects in these 5 experiments. So in conclusion, the main limitations that we identify in this paper are the evaluation of the method using only this one data set, that may put into question the accuracy when applied to other contexts. Although the data set has a reasonable number of projects, we would like to run more experiments or on even more projects with different contexts, different domains that use different development methodologies, and that came from a company environment, in order to increase the confidence in the results obtained and reported here. The second limitation we identified was our assumption that made in the effort forecasting approach, where we assume that the developer works the same amount of time per hour on all its assigned user stories, what may not represent the reality, and also that the developer only works 8 hours a day. That could also not be true. Also, the use of the mean magnitude relative error as an accuracy indicator, since despite being widely used for this purpose, it suffers from some drawbacks, as being a symmetric indicator, meaning that it underestimates cannot exceed 100%, whereas overestimates are unbound. And it is also a dispersion measure. These characteristics that make it problematic when dealing with error compensation, like the case. And finally, we did no comparison against other methods to compare the accuracy of the method, what could represent a valuable discussion to make, as it can give us practical evidence of which method provides better accuracy and smaller errors in each case. The main observations that we take from this paper are that the results shown suggest that when we look too much into the future, forecasts start to get less accurate, since the further we look into the future, more errors will accumulate. This may happen due to the accumulation of errors, as more user stories need to be considered in the forecast, or to the accumulation of changes in the context of the project that imply a different delivery behavior, such as changes in the constitution of the team, gains of experience by the team in specific technologies they are working with. And the second main observation is that we could observe that some of the characteristics that make the Monte Carlo method so apt to be used in agile contexts are its simplicity to be applicable, its easy to understand, and its granularity. As future work, we would like to implement a machine learning method due to the possibility of discover existing patterns between projects, the avoidance of overfitting to data, and the generalization capability inherent to these type of methods. The results of this study can be used as a baseline to evaluate other methods and compare the results. It can be used particularly as a baseline for a study using machine learning methods. The takt time and effort approaches are based on the findings to good delivery forecasts, data features that can be used on this machine learning implementation. That's all for me. Thank you very much to hear this presentation, and goodbye.